As we can see, the modern periodic table take care of a three limitation of a Mendeleev's periodic table. The anomalous position of a hydrogen can be discussed after we see what are the bases on which the position of an element in the modern periodic table depend. Okay, what okay in which position that the periodic table is totally depend. Okay, depending on that, okay, we can say that hydrogen position in a periodic table are still what okay pending. Okay, which where the hydrogen is placed so that it can satisfy its position. Okay, so still it is pending. Okay, so hydrogen position is not yet okay discussed that where it should be placed. Now position of elements in the modern periodic table. Okay, different positions are there of every elements. The modern periodic table has 18 vertical column known as a group. Okay, in a modern periodic table we can see that 18 vertical column is there, which we say it as what, say it as a groups. Okay, 18 groups are there, vertical column which is considered or are said to be what, okay, it is a group. And 7 horizontal row, how many rows are there, okay, 7 horizontal rows which are said to be what, okay, periods. Okay, which we say it as a periods. Okay, 7 horizontal rows are said to be periods, and 18 vertical column which are there is said to be what, okay, it is a group. Let us see what decide the placing of an element in certain group and period. You will find that all these elements contain a same number of valence electron. The element which are there having what, okay, same number of valence electron. Similarly, you will find that the elements present in the any one group have the same number of valence electron. Okay, if we see in a group that all the elements which are there in that particular group have what, okay, have a same number of valence electron. In that group, okay, the element which are present, they will contain what, okay, same valence electrons. What, okay, number of valence electron will be same in that group. Okay, for example, if we talk about that, for example, elements fluorine, chlorine belonging to the group 17. Okay, how many electron do fluorine and chlorine have in their outermost shell? Okay, hence we can say that group in the periodic table signify an identical outer cell electronic configuration. Okay, so here we can see that in a group, okay, if elements are present, that elements have what, okay, valence electron of that group containing elements, or an element which are present in a same group will have what, okay, same number of valence electron. Okay, so from this we can say that a group, okay, is one of what, okay, elements which contain a same valence electron, okay, in their outermost shell. Okay, so if elements which are present in the same group will have what, okay, will have same valence electron in their outermost cell. Okay, so on the other hand, the number of cells increase as we go down the group. As we go down the group, what will be seen, that the number of cell increases as we go down the group. Okay, so in all the elements you can see that on going down the group we will see that number of cell will increase, okay, in that elements. There is an anomaly when it comes to the position of hydrogen, because it can be placed either in the group first or group 17 in the first period. Can you say why? Because just now, okay, we have discussed that what, okay, hydrogen position is still pending. Why? Because it can react or it can act as what, okay, metal also, and it can act as a non-metal also. So you can see that it can be placed in a group first or group 17. Okay, wherever it should place, it can easily place because it contains both the characteristic as well as property, metallic also as well as non-metallic also. You will find that these elements of a second period do not have a same number of valence electron, okay, but they contain the same number of cell. Okay, now if we talk about that, okay, that elements which are present in a second period, okay, the elements which are present in a second period will do not have what, okay, same number of valence electron, but they will contain a same number of cell. Okay, the number of cell will be same, okay, whether it is in a K cell, L cell, M cell or N cell. Okay, so their cell will be a common. Okay, so the element which are present in the period, okay, second period, okay, do not have what, okay, same number of valence electron, but they contain what, okay, same number of cells. Okay, number of cells will be same. And you also observe that the number of valence cell electron increases by 1 unit. How? Okay, number of valence cell electron will increase by how many? Okay, 1 unit. By 1 unit it will increase as the atomic number increases, but 1 unit on the moving from left to right is in a period. Okay, so atomic number will increase by 1 unit from where? Okay, if we move from left to right in a period. Okay, in a period you can see that what, okay, if we move from left to right, its atomic number will increase. Okay, once again I am repeating. Okay, what, okay, we will observe, okay, we will observe that elements in a second period or any period, okay, do not have a what, okay, same number of valence electron, but they contain a same number of cell. What, the number of cell will be same. You also observe what, okay, we will also observe that the number of valence cell electron, okay, number of valence cell electron will increase by 1 unit, okay, as the atomic number increases by 1 unit on moving from left to right in a period. Okay, in a period, if we are moving from left to right, we will observe that 1 unit it will increase. It will increase by 1 unit, and valence electron will increase by 1 unit. So, if we move from left to right, we will observe that in a period, what? Okay, 1 unit will increase in atomic number. Atomic number will increase by 1 unit. Okay, or we can say that what? Okay, atoms of a different elements with the same number of occupied cell are placed in the same period. Sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon. Okay, as you can see that sodium, magnesium, aluminium, silicon, phosphorus, sulfur, chlorine and argon belonging to what? Okay, third period of a modern periodic table. It is belonging to where? Okay, third period of modern periodic table. And since the electron in the atom of this element are filled with what? Okay, K cell, L cell, M cell. Okay, it is filled in with what? Okay, it is filled in K cell, L cell, M cell and N cell. Okay, so KLM cell. Okay, write the electronic configuration of this element and confirm the above statement. Each period mark a new electronic cell getting filled. Okay, so in each period we will see what? Okay, new electronic cell will be filled. Okay, which we have already studied in a 9th standard also. That K cell, L cell, M cell and N cell. Okay, maximum electron in a K cell is how much? Okay, it is 2. Maximum electron in a L cell is how much? Okay, it is 8. maximum electronic configuration or a electron maximum electron can be filled in M cell is how much? Okay, it is what? Okay, it is 18. Okay, it is what? Okay, it is 18. How much? Okay, it is 18. Okay, so here you can see that maximum in a K cell, how many electron can be filled? Okay, it is 2. In a L cell, how many electron maximum it is filled? Okay, it is how much? Okay, it is 8. And for the M cell, maximum how many electron can be filled? Okay, it is how much? Okay, it is 18. Okay, so this way you can see that. Okay, how many electrons are there in the first, second, third and fourth period? We can explain the number. Okay, here it is already given. Okay, we can explain the number of elements in this period based on how electrons are filled into various cells. You will study the detail of this in a high classes. Recall that the maximum number of electrons that can accommodate in a cells depend on the formula 2n square, where n is what? Okay, number of a given cell from the nucleus. Okay, from the nucleus, what is the number of a cell? Okay, so here you can see that for the K cell, okay, which we have already discussed, it is maximum how many? Okay, 2. And for the L, it is how many? Okay, it is 8. Hence, the first period has 2 elements, and hence the second period has how many? Okay, it has how many? Okay, it has 8 elements. Okay, and the third, fourth, fifth, sixth, seventh period have how much? Okay, it is 8, 18, 18, 32, 32 elements respectively. Okay, so the reason for this you will study in higher classes. Okay, in higher classes we will study. Okay, once again I am repeating, in a K cell how many elements will be there? Okay, in K cell there will be what? Okay, first period, okay, which we say it is the first period, it is 2 elements. In the second period it is maximum 8 elements. For the third period it is maximum how many? Okay, 8 elements. And same way for the fourth it is how many? Okay, it is 18. Okay, for the fifth one it is also 18. For the sixth one it is 32, and for the seventh one it is 32 respectively. Okay, the position of an element in the periodic table tell us about its chemical reactivity. What? Okay, position of an element in a periodic table will tell us what? Okay, chemical reactivity. Okay, which type of chemical reactivity it contains. As you have done, the valence electron determine the kind and the number of bonds formed by an element. Can you now say why Mendeleev chose of formula of compound as the basis for deciding the position of an element in his table was a good one? How would this lead to an element with the similar chemical property been placed in the same group? Okay, so Mendeleev has made a what? Okay, group as well as period. Okay, depending on that elements are arranged. Now, trends in the modern periodic tables. Okay, first is what? Okay, first is valency. As you know, the valency of an element is determined by what? Okay, number of valence electron present in the outermost cell of its atom. Okay, what? Okay, valency is what? Okay, number of outermost or a number of valence electron present in the outermost cell of an atom. Okay, is said to be what? Okay, valency of that elements. Okay, so that was our valency, which we have already studied in ninth also. Same way, okay, here also we are studying that what? Okay, valency is what? Okay, number of what? Outermost. Okay, in outermost orbit, how many number of valence electron are present? Okay, that is considered to be valency. Now, atomic size. The term atomic size refer to the radius of an atom. Okay, atomic size is totally what? Okay, radius of an atom. The atomic size may be visualized as the distance between the center of the nucleus and the outermost cell of an isolated atom. Okay, atomic size means what? Okay, a distance between nucleus which are present exactly at the center and outermost cell of an isolated atom. Okay, outermost cell of a particular atom or isolated atom. Distance between these two are said to be what? Okay, atomic size. The atomic radius of a hydrogen atom is 37 picometer. Okay, pm, which we say it is a picometer, and 1 picometer is equal to how much? Okay, 1 picometer is equal to 10 raised to minus 12 meter. Let us study the variation of an atomic size in a group and in a period. You will see that the atomic radius decreases in moving from left to right. As we move from where? Okay, left to right. What? Okay, as we move from left to right, atomic radius decreases. Okay, along the period, and this is due to what? Okay, because of increase in the nuclear charge, which tend to pull the electron closer to the nucleus and reduce the size of a atom. What will be seen? Okay, because of a increase in the nuclear charge, what will be seen? That it will pull the electron closer to the nucleus, and due to which, okay, size of an atom will reduce. And you will see that the atomic size increases down the group, and as we go down in the group, atomic size will increases. This is because of a new cell are being added as we go down the group. As we go down in the group, we will see that new cell is added. Okay, so this increase the distance between the outermost electron and the nucleus, so that the atomic size increases in spite of increase in the nuclear charge. Okay, so this way you can see that what? Okay, because of addition of a new cells, okay, or a orbits, we will see that as we go down in a group, okay, valence electron or a outermost cell electron and nucleus distance will increase, due to which we will see that atomic size is also increases. And the metallic and non-metallic property. Now, as we can see, the metal like sodium and Mg, Na and Mg, sodium, which is Na, Mg means magnesium, okay, are towards the left hand side of a periodic table, while the non-metal like sulfur and chlorine are found in the right hand side. In the middle, we have silicon, which is classified as a semi-metal and metalloid because it exhibits some property of both metal and non-metal. In modern periodic table, zigzag lines separate metal from non-metal. Okay, in that periodic table we are seeing that there is a difference, or it is preparing a distinguish between metal, non-metal and metalloid. Metalloid means what? Okay, having both the characteristic, okay, which have semi-metal or metalloids. Okay, what? Okay, which is classified as a semi-metal or metalloids because it exhibits some property of both metal and non-metal. Okay, the borderline element boron, silicon, germanium, arsenic, antimony, tellurium, polonium are intermediate in property and are called to be metalloid or semi-metal. As you have seen in chapter 3, matter tend to lose electron while the forming bond. Okay, matter will what? Okay, lose the electron. Okay, lose the electron. Okay, while forming bond, that is they are electropositive in nature. They are electropositive in nature. Okay, as the effective nuclear charge, acting on the valence cell electron increases across the period, the tendency to lose electron will decreases down the group, and the effective nuclear charge experienced by the valence electron is decreasing because of the outermost electron are far away from the nucleus. Okay, from the nucleus you can see that electron are farther away, due to which you will see that what, okay, it will increase the distance, and therefore this can be lost easily, and it can easily lose. Hence, metallic characteristic decrease across the period and increase down in a group. So, the non-metal on the other hand are electronegative. They tend to form a bond by gaining electron. Okay, non-metal will gain electron. Okay, let us learn about the variation of these properties. Okay, as the tend in the electronegative, so non-metal are found on the right hand side of a periodic table towards the top. Okay, as we can see in a periodic table, and this can also help us to predict the nature of an oxide formed by the element, because it is known to you that the oxide of a metal are basic and the non-metal are acidic in general. Okay, which we have already studied in a previous chapter. Okay, what? Okay, oxide of a metal are basic and non-metal are acidic. Okay.
Periodic table put forth by Mendeleev was quite well defined, but it wasn't the best table ever. Why do I say so? It's because with time, the number of elements being discovered increased, and fitting them into the table according to the periodic law by Mendeleev seemed difficult. Also, we have taken a look at the major limitations of the periodic table by Mendeleev. So with all these limitations, how do we study the elements? How do we carry out the periodic classification? Well, if the elements discovered later did not follow the periodic law given by Mendeleev, then the only way to arrange them was by modifying the law. Yes, this was, however, not what scientists could think of as the first step. It was quite gradually that the scientists realized the fact that the law could be modified. But how did this happen? It was around 1913 that the British physicist Henry Moseley found an interesting fact. He realized that instead of atomic mass, all the elements will show periodicity if arranged on the basis of their atomic numbers. Wait a second, did I just say atomic number? Isn't atomic number a randomly assigned number to the atom by us? Actually not. Atomic number of any element is never a randomly assigned number. It is basically the number of protons present in the nucleus of the atom of that element. For instance, let us consider the first four elements in the table. So we get atomic numbers of hydrogen as 1, helium as 2, lithium as 3, and beryllium as 4. So why are these elements assigned these particular atomic numbers only? Can we change these numbers ever? No, we can't. That is because they have these respective numbers of protons in their nuclei. Hydrogen has just one proton in its nucleus. Similarly, helium has 2 and lithium has 3. And how many protons will beryllium have? Correct, it has 4 protons. The same is valid for other elements as well. Coming back to the table, did Henry Moseley think that characteristics of elements are based on their atomic numbers and not their atomic masses? Yes, that's what he meant. And with this, there emerged a new law of studying the periodicity of elements. It was called the modern periodic law. The law stated that the properties of elements are periodic functions of atomic numbers. So what does this mean? This means that the physical and chemical properties of elements do occur periodically. But this happens when the elements are arranged according to their atomic numbers. All the known elements could be arranged based on their atomic numbers. With this, predicting the properties of elements yet to be discovered got simpler and more precise. This helped in placing the newly discovered elements properly in the periodic table. Also, overcoming the limitations of Mendeleev's table was another advantage. And how did that happen? Do you remember the limitations? The first limitation of no precise position for hydrogen was mainly overcome. It was assigned a position that would not lead to any confusion. We will take a detailed look at this position of hydrogen later in the higher grades. Next limitation of the Mendeleev's table was the position of isotopes. Can you recollect what isotopes are? Yes, they are the atoms of the same element with different number of neutrons. That is the reason why, in spite of belonging to the same element, the atoms have different atomic masses. Because atomic mass is the sum total of all the protons and neutrons present in the nucleus. Placing isotopes in the table was a limitation. As we know, in the modern periodic table, the position of elements was no longer based on atomic masses. They were based on atomic numbers. An atomic number is given by the number of protons. That means the different number of neutrons will not be a worry for us. So it was possible to place the isotopes now. Because all the isotopes of any particular element could be placed at one single place. And this place would be the position of that element in the table. So now can we say that chlorine 35 and chlorine 37 will be placed together? They both have 17 protons, which means they will have the same atomic number. Hence, they will be placed together. Lastly, we had the prediction and placement of undiscovered elements. The previous table by Mendeleev was based on atomic masses of elements. However, the atomic masses of elements were not arranged in a constantly increasing order. Hence, if newly discovered elements were to be placed in the table, then their position would be confusing.